And welcome to Chapter 14, The Behavior of Gases. In this particular chapter, we're going to be taking a look at just that, the behavior of gases. We're going to review the kinetic molecular theory. We're going to take a look at the four parameters that describe a gas, the pressure, the volume, the temperature, and the numbers of moles. We're going to take a look at the relationships among those four parameters in the gas laws. We'll be doing calculations with those gas laws and introduce you to the idea of what's called the ideal gas law. And in the last section, we're going to be taking a look at properties of mixtures of gases, particularly with Dalton's law of partial pressures and also what's called Graham's law. Now, let's go ahead and jump in. In 14-1, we're going to take a look at some of the properties of gases, and we're going to start off with a review of the kinetic molecular theory, which comes from Chapter 13. The kinetic molecular theory basically says four things. First of all, it says that gas particles are hard spheres with insignificant volumes. Now, are they actually hard spheres? No, they actually have lots of different shapes. Do they have an insignificant volume? Well, it depends on the application. But again, when you're dealing with a model or a theory, you make these assumptions that simplify the process and simplify the relationships, and by doing so makes things a whole lot easier. Number two, it says that particles do not interact with one another. Do not interact with one another. Now, is that absolutely true? No. They actually do interact with one another to a small extent, but for the most part you could ignore that in the calculations. Number three, the motion of the particles is rapid, constant, and random. They fly around at high speeds. They're always in motion. They do not stop. And you really can't predict which direction they're going to be going at any one moment. They collide with one another and bounce in random fashion. And finally, number four, all collisions are perfectly elastic, meaning they do not lose energy when they collide with one another. They simply bounce off with the same total energy as before. For example, when pool balls start colliding with one another, they actually start to slow down due to the friction of the collision when they rub against one another. Plus, you have the friction of the felt of the pool table itself. We assume that when two particles collide, they actually don't slow one another down. All of the energy is conserved. Now, also from Chapter 13, we want to review the idea of pressure, because when we're taking a look at the parameters of pressure, volume, temperature, and the number of moles, we're most comfortable or most familiar with the idea of volume, temperature, and the number of moles. Pressure tends to be that one parameter that people need to be brushed up on. So, you have to remember that gas pressure results from the collision of the particles and we can say that it's the collision of the particles on the surface of the Earth, on the surface of an object, on the walls of a container. Whatever the case may be, the particles are hitting something other than just themselves. Okay? And you can measure this pressure with a device called a barometer. So let's go ahead and review how this thing works. Alright, so what you actually have is a tube of mercury. We're looking right here now. We have a tube of mercury that is flipped upside down in a pan of mercury. And so what happens is this mercury here in this tube wants to force its way out of the tube. In order to force its way out of the tube, it's going to have to raise the level of mercury in this pan. Now you also have the pressure from the atmosphere pushing down, as these red arrows are indicating. They're pressing down on the pan itself. So you have two forces pushing on each other: the force of the mercury pushing out and up on the mercury, and then the force of the atmosphere pressing down. And there is a pushing match here that will eventually come to a stalemate. Right now, the mercury is pushing out harder than the air is pushing down, so some of the mercury will force its way out of the tube. And so if you look at the tube on the left, on the right, the mercury is lower. All right. Now, on the other hand, if the pressure in the atmosphere pushes its way, if the pressure on the outside is greater, it can force the mercury back up into the tube, and the mercury will go higher in the tube. So what you're actually measuring is the pressure of the atmosphere. The higher the pressure is of the atmosphere, it's going to push down and force the mercury higher into the tube. The lower the pressure of the atmosphere, the mercury is going to force its way out and be lower in the tube. And so when you take a look at two scenarios, one at sea level and one on the top of Mount Everest, you have a greater pressure at sea level as on top of Mount Everest. Now, why is that? Well, let's go ahead and take a look. If this is sea level, and we'll draw Mount Everest right here. Okay, if you are standing at sea level, standing on top of the water there, you have, and we'll just say this is the top of the atmosphere. You have the entire weight of the atmosphere above you pressing down on you. When you are on top of Mount Everest, here you are, you only have part of the atmosphere pressing down on you. So you have a much larger amount of air pressing down at sea level as you do when you're on top of Mount Everest. And that's reflective of these mercury levels in the tube. What happens is when you're at sea level, you're going to have a much higher pressure. And in fact, on average, the pressure at sea level is 760 millimeters of mercury, meaning the mercury level in the tube will be 760 millimeters high. On top of Mount Everest, that value is only 253 millimeters of mercury because you only have a little bit of air pressing down on you or pressing down on this pan. Now, because that 760 millimeters of mercury is the average pressure at sea level, we say that that is equal to 1 atmosphere, because you have 1 atmosphere, and I'm going to abbreviate it ATM, pressing down on you. So as it turns out, 1 atmosphere is going to be equal to 760 millimeters of mercury. And so if we take a look at some common units, we can say you have millimeters of mercury, so we'll just say 760 millimeters of mercury is our starting unit. That you can also call that torrs, 760 torrs. Torrs is short for Torricelli, which is the name of the scientist who developed the barometer, Evangelista Torricelli. That will be the same as 1 atmosphere of pressure. If you use physics to derive pressure, you can use a unit called pascals. 101,325 pascals is the same as 1 atmosphere, or 760 millimeters of mercury. If you change that into kilopascals by dividing by 1,000, it would be just 101.3. Or for those who are familiar with the American system, that would be the same as 14.7 pounds per square inch, or PSI. Alright, so you should be familiar with the idea of the kinetic molecular theory, and you should also be familiar with what gas pressure is and why we have the various units that we do. Alright, in the next podcast, we're going to take a look at how you can convert among the different gas pressure units. We'll see you next time.